Good morning, everyone. I am Matthew at M Team. I'm going to be coordinating some of the base native rollup stuff, excuse me. Um, we're just going to go up until the hour today and talk about native rollups. That will be the only time that is recorded. But after that, we'll have some unstructured time as well. I am the co-founder of Spire Labs. I'm very passionate about base rollups, and I believe that there's a really powerful union point between base rollups and native rollups that Justin's calling ultrasound rollups. I like that name, but some people don't. And the nice thing about ultrasound rollups is that they have essentially equivalent security properties to the layer one, but also have strong synchronous composability between the layer one. So feels like the kind of thing that we wanted sharding to be, but actually practical. So yeah, we're just gonna go around and do quick introductions, and I'm gonna ask you to explain like your conviction on native rollups and kind of what's specifically you're bullish on about native rollups so far. Just kind of take a couple minutes and go through that. Justin, do you want to start?
Yeah, sure. I mean, I guess shard could be another good term for based and native rollup. Although shard typically suggests an exact copy of the L1, and so maybe programmable shard is kind of another term that could be used. The reason why I'm super excited about native rollups is that they basically solve a bunch of problems for the rollup for the L2s. Number one is that you don't need to worry about bugs anymore if you want to be EVM equivalent. Like by construction, out of the box, you have an exact copy of whatever you have at the L1. So the validators are running clients and verifying state transitions, and the exact same validators would be running the exact same software to verify the state transitions happening at L2 in addition to the L1. The other thing I'm excited about is that native rollups solve the governance attack vector that a lot of the rollups have if they want to remain EVM equivalent. So today you can't have a immutable virtual machine which is long-term EVM equivalent, and the reason is that the EVM itself is a living thing, and it lives through social governance with hard forks. And so today what we have is like a multi-sig or some sort of token governance to remain EVM equivalent. Once you have this precompile which exposes the native EVM execution engine, it stays equivalent through hard forks. So that's a very nice feature to have. And then the final problem that I think native rollups solve is that they dramatically simplify synchronous composability. And the reason is that if you want to have synchronous composability with the L1, you need to have what I've been calling real-time proving. But real-time proving is maybe a term that I'll phase out a little bit in these more technical discussions. What I really mean is same slot proving. So the proof needs to arrive in the same slot as when the block is produced. And what you can do with these native rollups is that behind the scenes, you can use next slot proving, where basically the proof is delayed by one slot. And the reason is that I think the L1 is going to move to this model where the validators just accept blocks in slot N, optimistically, if you will, without executing them. And then they will only compute the state root in slot N+1. So this is a proposal by Dan Robinson and Charlie Noyes and Max Resnick. There isn't an EIP yet, but there will be an EIP, and it solves a lot of problems. And in particular, it also helps with the latency problem of real-time proving, shifting it from same slot to next slot proving.
All right, Joshua, do you want to go next?
Yeah, sure. So just quick introduction to myself. So I work in Mental Network. So Mental, MENTLE, originally it's one of the early L2 networks that started out using the OP stack. So we've been an optimistic sort of a rollup construction. We have actually worked with Succinct, and this is recent news from the end of last year that we're working on using their SP1 prover, their ZKVM prover, in order to take our existing rollup construction and architecture into a ZK validity proof a rollup. I think this helped us in a few ways. So we've been thinking a lot about trying to future proof the chain. It's very difficult to do state migration. So just to highlight that, that was one of the reasons why we ended up going down this route, was because it's very difficult to take the entire state and some customizations that we have in order to derive a new architecture. So the ability for us to use succinct snark proofs was sort of like a very quick fix in terms of a proving system, and also down the ZK route. Now, one of the reasons why we also were going down this route was because when we looked at the beam chain roadmap, I think another key part of our ecosystem is that on the L1, we also support a lot of validator infrastructure through liquid staking protocol. So we also have quite a number of operators and that operate validators, and we'll potentially also see the transformation of the staking requirements getting lower and lower as a result of this beam chain roadmap. So I think from this angle, we do see like a very, very strong interest to remain as compatible as possible down this roadmap. And is a kind of a living example of a big chain. So we're currently like probably on L2B, I think we're the fourth largest. And it's a good example of like a chain that's actively working with production level transactions, and people actually working with this set of tooling and trying to see how we can move that architecture across the beam chain roadmap into a state that like I call it like maximization of decentralization. So you have really low requirements for staking, and also maximization of maximization of decentralization and maximization of efficiency because of this succinct proofs where it's all one type of complexity, and you verify it, and it's quite stateless. So I think from there, like that's where I'm angling towards trying to understand how we can remain as much as future ready and as compatible looking forward.
Matthew, you're muted.
Oh, sorry. Ming, do you want to go next?
Yeah, hi everyone. Yeah, so I mean I work in the PSE, belong to the under Ethereum Foundation. So I'm working on the ZKVM like exploration. So or recently milestone is we try to explore some performance ZKVM prover, and basically this is more like a sum check based. So we are working with some working on some open source project with some L2 provider in the market to explore the performance ZKVM, what it will be look like, and basically it's like yeah, the technical stack. Yeah, and before we just kick off this project last year, and before that I'm working on the ZKEVM project, which also like under the PSE of Ethereum Foundation. So yeah, so I'm very excited about the native rollup because I think at least this one resolved the existing problem we have. And the ZK EVM project I have working on previously, the most challenging question is because EVM is very complex. So to make this EVM to be run in the ZKVM is also a very, very challenging task. So that's why so many people exploring that. And even for our team right now, we still explore what's the possible technical stack in the future, how to landing this kind of stuff in the mainnet. Yeah. So before that, I'm pretty aggressively thinking that probably in one day the mainnet, the block settlement can be just squeezed into one snark proof, and all the validator just verify it, then the block will be settled. So this one is more ambiguous. Sorry, the more aggressive plan, because this one involve you need to generate a proof in a very short time, because the Ethereum mainnet block they do need to be settled. They have a strong requirement for the block to be settled. So we need to generate a proof. So that's why we think the performance proof is very important to make this one happen in the future. Yeah, but native rollup is another, for me, it's another roadmap, because this one is basically probably share some common challenge for the ultimate goal for the ELO settlement. But for the native rollup, probably we can apply some, for example, one slot delay or some other tricks. So probably we can, it's kind of, for me, it's kind of the middle milestone to achieve the final goal. Yeah, so that's why I feel besides native rollup, because native, so it also means the EVM compatible, or everything is like the same as L1. Yeah, so the research or the effort we put probably can also be used in the native rollup. So yeah, that's why I also feel very excited about that. But today I also want to raise the question is, if in the future we try to make the single snark proof for the mainnet block settlement, then how does the native rollup play in this role? Because I feel like if the mainnet throughput is large enough, probably we don't need rollup. So the rollup exists because we want to improve the throughput by the rollup way. But what if the mainnet can be settled in a more like a high, like a snark or ZK way? Then do we still need a native rollup? So this is also one question in mind. Hopefully we can have some roughly discussion for today. Yeah. So basically this is what I'm working on and my introduction and my expectation. Yeah.
Awesome, thank you. We can hopefully get to that later. ALIZK, I don't know how to pronounce that, but would you like to go?
Yeah. Hello, I'm Ali from PSC as well. I work with Ming on the ZKVM project, but also other projects like folding and client-side proving and security. And I'm also a founder of ElectISEC, which does smart contract security and zero knowledge auditing as well. I guess I have been passionate about snarkifying Ethereum for a while, actually, since the rollup centric roadmap. One of the major concerns that I have is L1 losing its place as a deployment target. If it's only just a settlement layer, then eventually rollups will get big enough and break off, and we will lose this public good, which is Ethereum. While if Ethereum remains an execution layer as well, and a viable execution environment for at least some dApps, then everyone wins basically, including rollups themselves, because they get advantage, or they get to take advantage of interoperability and shared liquidity and a lot of the good things that shared sequencing is going to bring, for example. With respect to native rollups, I guess some of the gray areas that remains to me is how the plumbing of sequencing and execution happens, and things like that. So yeah, I am excited to get into the details of it. It's some of that, back-end things, if we call it, might still be unclear. I do agree with Ming that there is a lot of overlap between native rollups and snarkifying mainnet itself. Probably the only difference is probably the state, whether native rollups will be allowed to have their own customized ZK optimized state or not. But yeah, it will be also interesting from a coordination and focus point of view, where we think about something like that. And the other point that I am very interested in bringing attention to is auditing, and how we can make the right choices in order to compound auditing efforts, so that's, working on even the Beam or the mainnet snarkification or native rollups, they all have a shared component so that all these auditing efforts can be compounded and taken advantage of.
Thank you. Artem, do you want to go?
Sure. Hi, everyone. Good to meet you. My name is Artem. I work as a research lead. Just a moment. Yeah, I work as a research lead at Cyberfund. Cyberfund is an investment firm from founders of Lido, Konstantin and Vasily. And we're also Genesis investors in Ethereum. And as a result, we're super interested in basically everything related to Ethereum, from both infrastructure and applications. And naturally, we're interested in all the cutting innovation that's happening in the Ethereum infrastructure land, in particular native rollups. But yeah, so and talking about native rollups, this is a really cool idea in general. First of all, and for a long time, I'm really fascinated by this kind of trade-off that actually all businesses face at some point, which is either outsource some of their stuff or vertically integrate. So in this particular case, we're talking about rollups, which is basically scaling execution, but also maybe like some of the BD stuff. Onboarding users essentially. And yeah, in particular, also Ethereum's move to outsource everything to Rollup was really cool to me at that time. Let's say 3 or 4 years ago, it was a really non-trivial one. But I think right now it's sort of it's the right time to bring some of the things that are in rollups back to Ethereum L1. And I think native rollups is the technology which will allow this to happen. And the most important one is the network effects that that will come to native rollups. Actually, maybe probably to even based rollups via synchronous composability. Yeah. So, and also I want to highlight a couple aspects that are interesting to me. One is, is the coordination angle. How to get it off the ground. What's the right path towards the end game? Because I think the end game here, in some sense, there's some consensus. I mean, there's a question, of course, how many native rollups, and et cetera, but roughly speaking, this snarkified execution endgame is more or less clear, but the path towards it is what really is unclear. And so in my mind, for example, yeah, like native-based rollups, I think it would also make sense for them to be very close to Ethereum. And if they're just fully even deployed by Ethereum, then they would be shards. But maybe it could make sense for those rollups to share their execution fees, not 100% and not 0%. So right now, 0% shard would be 100%. It could be interesting to explore sharing a portion of execution fees with ETH holders, essentially burning ETH. So that's one aspect. I call them in my head such rollups aligned rollups. And then the second aspect is, another. There's like a sort of a bottleneck. I mean, in some sense, all core dev call is an extremely cool process, and the whole governance of Ethereum is what makes actually people confident in Ethereum. But it is a bottleneck in terms of kind of delivering changes. So I'm also interested in how can one potentially soft launch native rollups without hard forks, potentially via sidecars. And actually, Justin also mentioned like this cool idea that you don't even maybe need a snark verification first, and just do it via re-execution. And that would definitely also simplify things a lot. Yeah, thanks. Looking forward.
Thank you. Alex, you're last, I believe.
Yeah, so I think my day-to-day is leading the ZKVM form verification effort, and so I'm obviously particularly interested in the ZKVM angle to the native rollups. And I think other than that, like I'm very interested in trying to bring things back in touch with TL1 in terms of better composability and kind of running equivalent software. And I think Ali pointed out, just like you'd make a lot of auditing and security easier. And I'm kind of fully agree with that. I'm not going to reiterate too much on what I think Justin and Ali have said. I think I'm basically pretty much on board with everything they said. But I'm particularly excited in seeing, I think, where things will go, where native rollups will play a role in terms of adoption of ZKVMs, but also in terms of moving towards snarkifying DR1. And I think even how our maybe perception of native rollups and the role of rollups in the Ethereum ecosystem as we move towards kind of quite drastic changes to DR1 will shift. I think that isn't settled in stone, at least for me, and I'm quite interested in figuring that out.
Awesome. Thank you, everyone. I think there's some great people on this call. I get the sentiment that there's a lot of people that heard the native rollup idea and then were like convinced instantly because it sounds so nice. I think the open questions are around like specifications regarding like how does it actually work in practice, and then how do we go from the idea to the reality, and then that's obviously like a multi-year process that probably involves some external actors and then a layer one hard fork. So that's a tricky one for sure. So I do have a presentation, and I just want to go through and kind of discuss some of the important things that we've covered so far in the Telegram chat. Let's see. So, awesome. So here's what I want to go through. The first and kind of most important discussion point for me is to talk about some definitions. So the Justin put this in the native rollup chat, and it just goes through kind of a few overall definitions. Layer 2 for settlement, whatever settlement means. Rollup if it uses Ethereum DA, I think that's pretty obvious. Based if it uses Ethereum sequencing, which is again arbitrary and vague, and native if it uses Ethereum execution, which is the thing I want to address in this call. So I posed this question to the group: what is a native rollup? A few things to consider. It doesn't include ZK. If we're talking about re-execution, then probably not. Does it include the concept of like using blobs? Is that a part of the definition? And then I guess we can go from there.
Yeah, so my perspective on native rollups is that the subroutine that executes transactions basically uses a precompile which is exposed at the EVM. And this precompile is basically this execute precompile that you have in quotes here, all capitals, which takes several inputs. And the three, I guess, most important inputs are a pre-state root, a post-state root, and a trace. And basically what the precompile does is that it's making an assertion. It's asserting that if you execute the trace, starting from the pre-state root, you end on the post-state root. And so the precompile will either return true if that's a true statement, and it will return false if it's a false statement. And one of the subtleties here is that the trace needs to be available to the validators so that they have the ability to re-execute the the computation and verify that it's a correct state transition. And even if you don't use naive re-execution and you're relying on SNARKs, we still want the data to be available. And the reason is that we want anyone who wants to generate a SNARK to be able to generate a SNARK. I guess as a consequence of this, if we are basically requiring the trace to be available, it becomes a rollup. So by construction, you can only have native rollups. You can't have native validiums. If we basically go with this constraint that the trace needs to be available. Now, I guess the simplest kind of native rollup is one where all of the execution goes through this precompile, but part of the value of having programmability is that you can add logic around it. So you could imagine having a custom gas token or custom governance, or maybe you could have special system transactions that don't go through this precompile necessarily. They kind of get filtered out and executed in some different virtual machine. But so long as for the default path, I guess, for user transactions is to go through this precompile, I think that's sufficient for rollup to be called native.
Awesome, thank you, Justin. Are there any other suggestions for definitions? I think that covers it. Cool. The way that I would kind of approach this is not just defining things, but also talking about some terminology as well. That's something we failed to do for base rollups, I believe, for the most part, and that was very tricky for writing some of the first research write-ups, because everyone uses different words to talk about the same thing. So one thing I want to introduce here is a native execution precompile to refer to the precompile that is a requirement in Justin's definition to be a part of the subroutine, again, the default path for user transactions for execution on a rollup. And then I also suggest we kind of use as a placeholder the opcode execute. All right, is there any kind of suggestions on that or considerations?
I mean, another way to describe the precompile is to use terminology that we used many years ago, which is execution engine. So basically, this precompile exposes the EVM execution engine. And you could imagine exposing a different type of virtual machine, such as RISC-V, or even a WASM execution engine, or whatever it is. So if we want to use a different term for the precompile and the rollups that use the precompile, we could, if we wanted to, use execution engine precompile and native rollup, and so it's very clear what we're talking about at any given point in time.
Yeah, I like that. All right, so I don't want to spend too long in any one of these, so we'll just go to the next one real quick. Talk about ZKVM diversity. So this is something Justin put in the native rollup chat again, and the summary that I got from this is that while it may be valuable to kind of work on multiple ZKVMs simultaneously and even support like minority ZKVMs, there's kind of an unfortunate fact of life when it comes to the kind of soundness bugs that you see in ZKVMs, and that problem is that if you can break it in any point, it can break the soundness of the entire thing. And so and things like client diversity bugs kind of appear in different places in the client. Maybe there's one in the execution, the consensus, or whatever. And so if you have multiple implementations, it's unlikely that they'll have the exact same bug. But for ZKVMs, they can have a completely different bug in implementation, but still have the same end effect of kind of not being sound. And so I think it's likely valuable to formally verify at least one ZKVM and kind of enshrine the idea of that ZKVM, either on-chain or just off-chain with kind of social consensus. This is like the downside of this is that it takes longer to formally verify things. It's not easy, but I think there's some significant benefits as well. So I just want to open up to conversation if anyone has any ideas surrounding this.
So there is like one big benefit of the ZK approach is that you can very, very cheaply run multiple clients in parallel. Like if you take a default, typical operator on Ethereum, they will run one execution client, ref or gef or whatever it is. But there are like some really sophisticated, I guess, institutional operators who are running vouch that allows them to multiplex and run multiple execution clients, and then they can have some sort of a logic which says if 2 of the execution clients agree, 2 out of 3, for example, then that's kind of considered to be the truth. And with ZK, it's much easier to have a vouch style multiplexing, and so this to a very large extent, I guess, counterbalances the fact that if you have a ZKVM bug, it might just compromise the whole ZKVM, and so you can't trust it at all. So there are like still some compounding. If you're running, 3 as an operator, 3 ZKELs, and there's a probability, a P of each one being compromised, then you get P to the power 3, that all of them are compromised. And if P is sufficiently low and the exponent is sufficiently high, then actually maybe we're good. And so what I would kind of encourage the validator operators to do is not just pick one client, but actually pick a whole set of clients that they trust.
Go ahead, Artem. Sorry.
Yeah, this might be a super basic question, but I had the following in mind. If there's multiple ZKVMs, it means that there's multiple proof systems. And I'm wondering, how can there be only one precompile but many proof systems? Because if some sort of proof builder, proves a block, they use a particular system. So attesters proposers who need to sort of verify this block, they need to have that particular proof system, if I understand correctly, in order to snark proof the block. So I'm wondering, how can there be only one precompile but many ZKVMs?
Yeah, so this is basically very similar to Ethereum and EVM today. There's only one Ethereum, one EVM, but there's 5 execution clients. And the key thing for the native rollups is that the execution engine precompile doesn't take in a proof explicitly on chain. So the proof is not one of the inputs that's made explicit on chain. Instead, it's implicit and it's gossiped off chain in some sort of peer-to-peer network. And so you could imagine that each execution client, gef or ref, becomes a ZK client. And so you have ZK gef and ZK ref. And as you said, each of these will have different choices of snarkification. They might use a different proof system or a different ZKVM or a different compiler that will take high-level code that compiles down to the ZKVM. And ultimately, what we need is for every single proof that's generated, for it to be generated for all of the relevant ZKELs. So there's multiple proofs that are generated, and the validators basically pick the subset of proofs that they feel comfortable considering to be trustworthy.
I see. So it's really proof builders need to basically generate all the proofs of existing proof systems on execution clients within the validators. Got it.
Yeah, and just to kind of reiterate, that set of proof systems is not like enforced on chain or not enforced in a hard fork. It's kind of up to the validators to choose which proof systems they want a proof to be generated for. There's kind of some like rough consensus that we have to build. Cool.
And there's a few key advantages to this approach. One of them is that there's a lot less complexity that we have to enshrine. right? It's all of the complexities kind of off-chain at the fork choice level, subjective to every single validator. And another one is that the Ethereum layer 1 doesn't have to pick a favorite, right? We don't have to pick SP1 or REST0. So there's a bit more credible neutrality. There's also much more diversity, right? If we were to put all our eggs in one proof system and there's a bug, then all of Ethereum fails. So it's reusing this robustness through client diversity approach. And then if we find optimizations to the proof systems, then those can be incorporated without a hard fork. The operators just need to update the ZKEL. And similarly, if there's a bug, right? If there's a bug in one of the ZKELs, for example, ZKGEF, well, all of those operators just need to update without a hard fork. So I think, given the amount of complexity that we're talking about with ZKVMs, this is the only kind of short-term viable path forward to not enshrine it and instead make use of diversity.
Yeah, thanks, Justin. Okay, let's go on to gas. So this is something I think is kind of not talked about enough for some of the native rollup related things, at least in my conversations, and that would be kind of related to the resource usage of native rollups. And there's a few key things to consider. Like, first of all, the proof generation stage gets more expensive and slower when you have to prove more per rollup and overall. So it's kind of more expensive if you have to prove a lot of smaller native rollups, but you can parallelize those, so maybe it's not too slow. But if it's one huge native rollup, then that is painful in terms of proving latency. And so there's a few things to consider here, especially if we're doing multiple ZKVMs related to proving cost. But I think that there's also some other reasons to kind of target certain gas prices. And so the kind of fee mechanism used to do this is going to be tricky. So Justin wrote this in the native rollup chat again, and this is just kind of going through the idea of using a global gas target versus a non kind of like individualized or granular gas target. So do you have any kind of thoughts on this or any important things to point out here?
I mean, one thing you point out, Matthew, is that native execution is going to be a limited resource. And the reason is that we need to have the provers be able to generate all of these proofs in a certain amount of time within one slot, for example. And this needs to be a credible minority prover assumption. So it needs to be credible that there's entities out there that are willing to do the proofs. And if in order to do the proving requires a data center, for example, this assumption is no longer credible. So what I'm hoping, I guess the ideal is that we're in a position where the proving can be done by entities with laptops, for example, and as such we need to have some sort of limit on the cumulative gas used across all of the different native rollups. And this is a recent realization that actually there is an incentive compatible mechanism to price this finite resource, which is simply to have an EIP 1559 mechanism, but not granular to an individual rollup, because in some sense there isn't such a thing, right? Like the precompile that asserts state transition functions is ephemeral. There is no notion of state that is long lasting, and so it's very difficult to charge an individual rollup. But if you charge all of the rollups as a group, then it becomes totally doable. And it kind of goes as well to one of the comments that was made, possibly by Artem, that maybe there's this model where part of the fees go to ETH and part of the fees go to the L2 token, and that would be one way to do it there, where you kind of have a base fee for native rollup execution, and that's the same for every single rollup. And then if you have some native rollups that distinguish themselves, because of whatever reason, then they can charge a premium on top of that.
Yeah, I mean, I'll add here the other kind of perspective for value pool for Ethereum is blob related. One kind of side effect of the kind of execution engine precompile that we've been talking about so far is that they can't do state diffs. They have to have like the full transaction data, and so they are purchasing a ton of blobs. And so I believe the blob market is like, we introduce a lot of demand from this. That is another conversation for another time. Let's talk about re-executions. This is kind of a less endgame thing and more like stepping stone related thing. I think the takeaway for me is that we can do native rollups, figure out an opcode to have an execution engine precompile, and expose this to rollups, start to get like specs out, create like a credible migration path. But instead of doing snarks and actually getting all of the scaling benefits, we can just get some of them with re-execution. And the beautiful thing about this is twofold. The first is that the kind of impact on validators in terms of like hardware requirements or bandwidth requirements is pretty minimal. You just need to think about an additional kind of like thread of execution. Other than that, state and bandwidth stay like roughly the same. I think it's really powerful. And then the second part is related to upgrades. So if we want to move to snarks in the future, which I think we do, then this wouldn't require a layer 1 hard fork if we already have what we're describing here, like re-execution. And so first of all, I want to ask, like, does anyone have any questions about like how re-execution would work and like how the migration process would work? Cool. And then are there any kind of broader discussions about like how wise it would be to attempt re-execution before snarks? I'll add one thing here, which is that Justin tells me that it may be possible to get native rollups in Fusaka in early 2026, and so that'd be incredible if we can make that happen.
So
Yeah,
maybe a bit more.
Go ahead, Ali.
So I wanted to clarify because I see like two notions of native rollups. So the first notion, which is relates to the old idea of having an enshrined shard, is that the native rollup is enshrined because you have a precompile, a verifier, which automatically means you have to enshrine a specific verifier, which ends up you selecting a proof system. But here I also see another notion, which is L1 is sort of coordinating basically around this precompile, which is sort of an interface that a native rollup would provide its own verifier, bring your own verifier to L1. And in that paradigm, we can have a diversity of native rollups because each will bring their own. They will tell the L1 nodes which verifier to use, basically. So I'm wondering which notion are we talking about? Is it like I don't see the first one, the coordinating part. I am not sure about it being a stepping stone to coordinating around an interface to enshrining specific verifiers.
So I guess there's three different models that you can go towards. The first one is that you have a very opinionated proof system, and that's the thing that's enshrined, and that's the thing that every single validator needs to run. I think that directionally, this is something that's very, very difficult to pull off in the short and medium term. And if anything, for questions of security, right? If there is even a single catastrophic vulnerability in whatever proof system was chosen, then that compromises all of Ethereum. It kind of goes against the client diversity ethos that we have. So the second path, which is I guess the one that was suggested by Vitalik, which is kind of this really clever idea, which is that the proofs don't go on chain. The proofs instead are gossiped off chain to the validators. We have a, you know, all of the validators have this kind of abstract notion of, you know, the EVM that's basically, you know, the yellow paper or, you know, the Python executable specs. But then the actual proof systems that are and execution clients that basically take this abstract notion of the EVM and kind of implement it in real life. All of this is implementation detail, and every validator subjectively makes a choice as to which execution engine they run or which ZK execution engine, execution client they run. And then there's a third thing that you're talking about, which is where the rollups kind of choose what verifier they have, which is the status quo that we have today with the ZK rollups. And the problem there is that, you know, that they're not native. And you know, there's all sorts of issues around potentially having bugs in whatever they've chosen, or the need for governance in order to keep updating the verifiers. So I guess what we're trying to do is take the status quo where each rollup decides its own verifier, and instead having this precompile that is meant to be an exact copy of the L1 EVM, but the choice is actually at the validator level, is not at the rollup level, if that makes sense.
Cool. Any more thoughts on like re-execution related things? Awesome. Let's go on. This is kind of a, I don't know how useful this slide is, but essentially Justin talked a second ago about kind of what the opcode might look like, kind of a rough specification. Justin and I also talked about this before, and this is kind of the kind of rough idea that we had, which was these three inputs. You have a pre-state root, a trace, which is just enough information to anyone to generate a snark proof, and the idea about the trace, and I could write more about it, but you essentially have like the full path of execution here. And then the bytecode input as well. So if we expose a kind of a RISC-V VM, and we would like to use the you know, this as underlying layer, but we want to agree on some EVM bytecode that can be used directly by native rollups and not to like bring their own bytecode, then we could have a kind of a contract that's made available. We just doesn't have to be a real contract; it could just be kind of included in the hard fork. And it can be referenced by the native rollup is the kind of simple idea here. And then the output is one of two things. You can have either a post-state root or an exception if there's some sort of kind of invalid execution that is impossible to prove. And so these are the two kind of possible results of this opcode. And yeah, I mean, we had a few discussions around like using blobs or state for bytecode. I think there's some trade-offs either way. Just I don't know if you have any kind of revised thoughts since this call, or if we want to talk a little bit more about this.
Yeah, I guess I have a couple minor revisions. The first one is that we need to expose the total amount of gas used if we're going to have this EIP 1559 mechanism. So in addition to the post-state root, I think it's good to explicitly expose the total amount of gas used in that specific state transition. And then the other kind of slight change that I have is that basically instead of putting the post-state root as an output, right now what I'm thinking of is just, you know, putting it as an input, and basically thinking of the opcode as being an assertion and basically returning true or false. Yeah, it's a bit of a minor technical detail, but like one of the questions is, do we want our proof system to be able to only prove correct state transition functions, or do we also expect the proof system to prove in basically proofs of invalidity of state transitions. And depending on which flavor we go with, we want to have these potential reversions of not. But I guess that's too in the weed. I guess the most important thing is just adding this gas used as an input or an output.
Go ahead, Adam.
Yeah, I was wondering about this 1559 idea. It makes sense to have it when there is like a clear, I guess, demand and also supply. And for me, I'm not sure, like if this opcode execute is, let's say, a third resource in Ethereum that is priced as 1559. If it's not done with via snarks, just by re-execution, it will obviously be a limited resource. But then if it is upgraded to snarks, is it going to be that different from like an addition operation on Ethereum? Like it seems it's going to be pretty cheap to verify.
Yeah, so the bottleneck will shift from the verifiers. You're right, it will be so cheap to verify that it won't be a bottleneck for the validators. But there's a new bottleneck, which is the prover. So I think there needs to be some sort of a gas limit. And actually, one thing that comes to mind is that if we do make the current L1 EVM instance snarkified under the same paradigm, then we can just unify the EIP 1559 mechanism. So instead of having a separate gas limit for the L1 and for the native rollups, we could just have a unified cumulative gas limit. And basically, the current EVM instance would become a native rollup. Actually, it would become more than a native rollup. It would become the first Ethereum shard, I guess.
Yeah, makes sense.
Josh, go ahead.
Yeah, I think to follow up to Artem's question, so I think earlier we mentioned the bottleneck will be shifting towards the provers, and I would believe the prover infrastructure is fundamentally very different from validators. Would there be? I mean, is the thought around this a new set of incentives for provers, in order to keep it, keep that going in an independent fashion, will there be sort of a separate set of infrastructure incentives in order to keep this in a finite set, and so forth?
Yeah, so incentivization is very important, and it's not a super trivial problem. The best idea that I have right now is that basically with attester proposer separation, we have two different types of proposers. We have the beacon proposers, who are assumed to be very, very weak, running on smartwatches or Raspberry Pis. And then you have the execution proposers, who are meant to be very sophisticated. Think of them as today's builders. And basically, we want the proving load to fall on these more sophisticated entities. We certainly can't have the proving be done on the Raspberry Pis. And one of the models basically is to have the execution proposers be bonded. For example, have a 1 ETH bond, and require them to produce the proofs, sufficiently many proofs, so that their block gets included on chain. So basically, they need to produce sufficiently many proofs to cover a sufficiently large subset of the validators, of the attesters, who will attest to their block and include their block on chain. And if we basically set the bond to be significantly larger than the cost of proving, then these rational entities are always incentivized to get these these proof built so that they can, at the very least, include their block on chain. And my guess is that for any given 12-second slot or 4-second slot or whatever it is, the proving cost will be very, very small, on the order of dollars, of total energy consumed or GPU time consumed or whatever it is. And so if we have a 1 ETH bond, that should be more than enough to incentivize the generation of the proofs. The slightly kind of unsatisfactory part of this answer is that there's only incentives to generate proofs for a majority of attesters. So if there's some sort of 1% of attesters who's running some exotic client, then they're not incentivized to pay the few cents or few dollars to generate the proofs for this 1%. Maybe one way to partially address that is one of the comments that I made earlier, which is that actually we want the validators to be running a plurality of clients. And so in some sense, there no longer are minority clients, because all of the operators are running most of the clients. And so every client is a majority client.
Oh, makes total sense.
Awesome, thank you, Justin. Let's get through our last couple of slides here. We're coming up on time. So this is one that's very important to me, and I want to talk about like kind of composability. So this is another note I took from a call with Justin a couple of weeks ago, and the simple idea is that this is part of a longer discussion about when do you actually need the proofs for a native rollup. If proof generation is still like in the order of minutes, then you can essentially just wait to kind of generate the proof until much later. But this is kind of something I want to skip over for now and have like a kind of a dedicated call for, because we're running out of time. The key kind of property that I want to look at is how base sequencing and native execution work together. We call it ultrasound, but let's imagine that it is we use it for composability primarily. I think that's the key benefit. This phrase kind of next slot proven, me and Justin used to describe kind of the native rollup property where you can provide a proof like after the block is proposed almost. And this gives you more time for proof generation, right? So one of the bottlenecks for base rollups and kind of working on proving is this proving latency. And the reason for that is because the more the proving latency, then the less time you have to build a block and to like get order flow, right? And so there's a ton of incentives to like encourage minimization of proving latency, but it's also very tricky because if there's like a massive advantage to having lower proving latency, then you kind of do have a centralization risk where one like super beefy prover, maybe run by a builder, has an advantage. There's a whole bunch of other things to consider there. But that brings us to plans for future calls. So these are kind of the things that I've thought about that would be useful to myself, and I do want to get some kind of outside opinions here. I'm gonna run some polls in the Telegram chat. But one thing I want to talk about is kind of rough speccing for an opcode, and not like trying to write up an EIP or anything, but just focus on what are the kind of what's like a unified understanding of the execution engine opcode that we can think about for our kind of future research. And then another one is gas and resource usage. So this is one we talked about a little bit here, but how all of the mechanisms that we're thinking about for gas play into the native rollup kind of opcode itself and other considerations as well. One thing I might bring up is that like I think the aggregate gas for all the native rollups doesn't like accurately represent the proving costs for all the rollups, because you could have a situation where you have many small native rollups, and that's faster to prove because the proving latency can be kind of parallelized. But if you have one huge native rollup, maybe the same aggregate gas, but have the downside of you need to kind of prove it sequentially. So there's a few kind of more complexities there. And then another one here is kind of incentivization of the provers. And this is one we talked about a little bit here. It's not only incentivizing provers to exist, but also encouraging them to prove for certain, maybe minority ZKVMs is a whole nother discussion as well. And then talking about migration as well. So this is where we talk about like migration from one version of native rollups to another, using like a different bytecode for that. We also talk about like doing a hard fork with the existence of native rollups. So if the EVM changes, then how does a native rollup kind of hard fork with that? It seems like we might need to use a 2-block fork process, which would be interesting. And then some of the incentives surrounding migration. So this is the other type of migration, which is going from non-native to being native. And so I think this would be a just, kind of a topic to discuss, and one that I think is going to be tricky, but with the right social pressures in place and the right building like a really good product when it comes to native execution, I think will give us a pretty massive advantage. So this is all the kind of stuff I had for today. This is about on time here, but I'll give us a couple minutes for any closing comments. Do we have anything?
I had a quick question about state on the opcode slide. Justin, where does the state live exactly? Is it in the trace always, or?
Yeah, great question. So it's in the trace. It's basically stateless execution. So the trace needs to include basically Merkle paths or Verkle paths, or at the very least, the state leaves that are being accessed. I guess the Merkle paths can be compressed. Actually, no, they can't be compressed, and the reason is that it's basically the comment that Matthew made, which is that we can't do state diff compression because we need everyone to be able to generate the proofs, and if you don't have the full witness, then you can't generate the proof. So one of the comments I guess that was made was that maybe we can have native rollups not in Fusaka in 2026 if we don't rely on snarks. I guess the biggest bottleneck to getting that precompile, technically speaking, is probably to agree on some sort of a format for statelessness. Like how do we communicate the Merkle paths and serialize them and get them on chain and put them in blobs or call data or whatever it is. So in some sense, standardization on a format for statelessness is a dependency to having native rollups in Fusaka.
Awesome, thank you, Justin. I'm going to stop sharing and then stop the recording. Thank you all for coming. This has been great.